Y nos quedamos a dormir donde sea que vaya. Y ahí en mi casa lo vamos a tu casa. ¿Tu casa qué? ¿En qué casa lo vamos a poner? Eso no puede estar mi compadre. Ahí pues. Pero nos quedamos a dormir.
A mí me tienen que dar un destino.
Pero nos quedamos a dormir. No, la puerta de color. Aguanta, pero eso no hacemos un sábado. A ver si me lo no lleves nada. Ay, nadie puede tomar fotos. Eso es una buena regla.
No, quiero tomar fotos.
No, es peligroso.
Pero ¿qué quiero que subir? Pero es chévere.
No, de una, esa es una regla. Entra, no puedes tomar fotos.
Todas fotos se has borrado. Hacemos el mega final larguísimo.
No, pues a las manos, los chicos borran.
Sí, pues para hacernos dejarlo y me vamos a recordar. Imagínate que nos quieran matar, no sabemos qué pasó.
Y lo hacemos un sábado y nos quedamos a dormir.
We leave our exercise, our applications for a moment and go back to the theory. Then we go back to application. Okay, now we were talking about diffraction. So we have this point B. And radius A. We found after some efforts that the absolute value of the electric field in that point is, sorry, we found actually, we will work out the absolute value in a moment. You already have this equation. On your notes. That's where we arrive. Okay, now we are really interested in the amplitude of the electric field. This is going to be absolute value of the field that would exist in free space. Please remember that the incident field is coming, the wave is coming that way, that is amplitude. The absolute value of this thing is 1, because this is the complex number whose absolute value is 1. And then we have this now. If you plot this function using whatever software you want, MATLAB or whatever, as a function of the aperture of our diaphragm, you will find something interesting. And here we plot the absolute value of the electric field. what you find is when the diaphragm, the aperture is 0, obviously this thing is -1. And the total electric field will be 0. This is has to be expected because if there is no hole, the field on the other side must be 0. Then you start opening your diaphragm a little bit, and the electric field in this point, we are calculating the electric field in this point, increases as you expect it to do. And it reaches a maximum value when this number is -1, because when this is -1, this is 1 plus 1, and this is the maximum value that you can achieve. This means that this happens when this argument is equal to B. And if we remember that beta is 2B divided by lambda, you find that the maximum is found when the aperture is square root of the wavelength times the distance. And what is the value of the field in that point? Since this is equal to -1, this is equal to 2, and so you find that a value of the field that is 2 times the electric field that is before the aperture. So in this point, you have an electric field that is actually stronger than the one you would have without, in free space, without the screen and hole. What's happening is that this aperture is focusing, like a lens, is focusing the electric field in that point. And then something else happens, because when you increase further the dimension of the aperture, this number starts to decrease. So you open a little bit more your hole, and the electrical field actually decreases. And there is a value of the aperture where the electric field is 0. And this value is obviously you can find that by imposing that this argument is equal to A. This is a minimum. Because in this case, this exponential is equal to 1, and you find 1 minus 1 equal to 0. And the things go on like that for a while. Then something happens. I'm not going into the details of this, but when the aperture becomes larger and larger and larger, this electric field actually stops oscillating. And it will eventually converge to a value that is E0, the value in free space. This is intuitive, because when your aperture is very, very large, it's like really free space. So you must somewhere converge to the free space value. Okay, but let us concentrate on those very first oscillations. In particular, please know that this value of aperture corresponds to a phase delay if you look at the equation that we have already seen. And this is a phase delay of this is a maximum phase delay. What do I mean? If you remember the picture that we drew, what I call maximum phase delay is the difference in phase between this contribution and the contributions that come from the points that are further away. That is the maximum difference. Further contributions would be destructive. That is, if you keep on adding contributions, then you will move from this point downwards. So the last constructive contribution to the field is the one that corresponds to a phase delay of 180 degrees. We keep this in mind when we, as the next step, we move to a point that is closer, when also the source is closer to the aperture. We will see that in a moment. Questions? Okay, what changes with source is infinity, at infinite distance. That is, we are not considering a plane wave now, but we have a situation as follows. We have our temperature, and this time we have the source or the transmitter at point Q and the observer or receiver at point P. What changes with respect to the previous case? The difference is that obviously we don't have a plane wave this time because the source here is generating spherical waves. So there will be two contributions to the different path length. And as usual, we can consider these spherical surfaces. So this is R1, this time this is R2. And the extra path will be now given by two contributions, what we call delta 1, that I indicated here, and delta 2, that is indicated there. Obviously, this is also R1 up to here, and R1 up to here. So now we want to evaluate total path length difference. Between the direct path and this other part here. Obviously this is delta 1 plus delta 2. Is the sum of the two contributions. And for those two expressions we can use the usual parabolic approximation and find for delta 1 where rho is the usual distance from the axis. Delta 2 is the equivalent contribution for the other part. Now the only thing that changes with respect to the previous case is that the phase difference this time is and we want this phase difference, if we want to take into account only constructive contributions, we have to impose that this phase difference must be at maximum equal to 180, like the previous case. So it is slightly different, but if you think that beta is 2p divided by lambda, this translates in a simple consideration that the difference in path length must be at maximum half the wavelength. Now, if we call this point here S, then our equation is QS plus SP, that is the path from here to here and from here to here must be less or equal. Now I use just equal because I want to find the limit condition. Must be equal to QP plus. It's another way of writing this equation. Now, we will not go into the analytical details, but this equation is an ellipse. This is an equation of an ellipse on that plane. And of an ellipsoid if you plot it in 3D. If we draw this ellipse, of this ellipse, the points Q and P, Q is a focus and P is also a focus of the ellipse. So the two foci of the ellipse are Q and F, and Q and P. So if we draw this equation, for every possible point, we find something like this. All the points within this ellipse are the points whose phase difference is less or equal to P. All the points within this ellipse, but you have to think about this ellipse as a three-dimensional volume. You can rotate this 2D image around the axis. All the points inside this ellipse contribute the total field. Give a positive contribution to the total field if this is transmitting. All the points inside this ellipse give a contribution as Huygens sources to the field. So if you block, because you have obstacles, if you block part of this ellipse, the electric field at the receiver will be reduced. This is called first Fresnel ellipsoid. And when you design a radio system, the recommendation is to keep the first Fresnel ellipsoid, that is all this volume around the radio link, because the radio link is from point Q to point P, free from obstacles, if possible. We will do some practical applications of this. Now, what is the maximum duct size? What is the dimension of this Fresnel ellipsoid? Let's call this A. What is the semi-axis of the for the first Fresnel ellipsoid? We can obtain this information from this equation, because the maximum size of the ellipsoid is in the middle, so it's when R1 is equal to D divided by 2. If D is the distance between the transmitter and the receiver. So if you force R1 to be equal to R2 to be equal to D divided by 2, what you find is if we use the definition for remember we are using this equation. And if you replace R1, R2 with D divided by 2, you find rho max, that is also what we call A, equal to the square root lambda T divided by 2. So this is the size of the maximum size of the first Fresnel ellipsoid. And you should keep this volume free from obstacles if possible. Questions?
Can you explain again the ellipsoidal part, please?
The ellipsoid?
Yeah, can you explain again just that part where the first Fresnel ellipsoid?
Yes. We start from this relation, and as you can see, if you write this, let me write it in another way. If you write this by replacing with this, you find square divided R1 plus square divided R2 equal to lambda. I just cancelled all the factors. And you say, okay, if I want to draw this equation is what does it describe? This is the equation of an ellipsoid. It is exactly the same thing as here. So if you draw this equation on this plane, in other words, you want to know, you are drawing all those points, all those paths here, the length of this path is all the same. It is all equal to this plus lambda divided by 2. If you take all those points, the figure that you obtain is an ellipse. And the point Q and P are the two Cauchy fuegos. And you know that one of the properties of the fuegos of the ellipse is that all those paths have the same length. That's why. So the perimeter of the ellipse are the points for which the difference in path length is lambda divided by 2. All the points that are, for all the points that are internal, let me put it this way, delta 1 plus delta 2 is less than lambda divided by 2. All the points on the perimeter of the ellipse they have delta 1 plus delta 2 equal to lambda menti, lambda divided by 2, and all the points external to this ellipse have delta 1 plus delta 2 greater than lambda. So if we want to consider only the points that give a positive contribution to the total field, that is, all the points, if you think about the previous case, all the points that contribute to the electric field up to the maximum value that we can obtain before starting to go down, all those points are inside the ellipse because the path difference is less than lambda divided by 2. That is, the phase difference is less than 180 degrees. Hope it is a little bit clearer now. If not, I can explain it again. But it really comes from what we have said about the contributions of the Huygens equivalence. Did it help or not? Yes.
I mean, this is a property. US by plus SP equal.
It's another way of writing this. The difference must be, because this plus this minus this is a difference. So it's just another way of writing it. The difference in path must be less or equal to lambda divided by 2. Yes, I understand the surprise. More questions? Okay, there is one last step we have to do. If we calculate the phase difference, that's beta times delta 1 plus delta 2. There is 2p divided by lambda R1 plus R2 no square. It just comes from manipulating this and multiplying by beta. This is quite often rewritten as follows. This is a typical way that we rewrite it, where this parameter v has got this expression. We will use this parameter in planning of radio systems. This is called Fresnel-Kirchhoff diffraction parameter. And you will find it, you will encounter it quite soon. We will encounter this parameter often when we calculate the effect of diffraction. Okay. This was the basic theory, really, very simplified, of the of diffraction. We will learn how to apply this to practical problems when we do the application part, the so-called exercise, really application. The next step is to see what happens when you don't have a hole. This can happen, but it's not frequent. This kind of behavior, for example, describes the electrical, what happens when you have a closed environment like this, and you have windows, for example. This kind of model works pretty well for windows. For example, if you are concerned about the exposure of people to electromagnetic fields, I don't know in Ecuador, but in Italy we have now quite strict laws for people exposure to electromagnetic field. In particular, we have a limit of 6 volts per meter inside buildings. And what happens? Have you seen that? I showed you that if you are unlucky, the electrical field in the point, but in this case, the electromagnetic waves will be coming from the outside world. So the point P is inside the building. The electric field inside the building can be 2 times the electric field that you have outside the building. You cannot take for granted that the electric field inside the building is weaker than what is outside. On average, this is true. But you can have some focusing effect in certain points. And if you have more than one window, for example, you have a series of windows, periodic series of windows, all those effects can accumulate. And you can have some hot spots inside your environment where you can have an electric field that is substantially stronger than what you have outside. and from let's say legislation or law point of view, this can be a problem. But this is one example. Another kind of diffraction that we find is when you have a plane obstacle that blocks your electromagnetic wave. We talked about this, I introduced them this morning. They are the so-called knife edge obstacles. And that's what we are going to see now. Questions so far on this kind of situation? Okay. Okay, knife edge diffraction is something that we find in this kind of situation. You have a transmitter. You have a receiver, and somewhere along the path you have an obstacle that is very thin, very sharp. Then we see what happens with rounded obstacles. But it's very thin and very sharp. The blocks may block the direct path between transmitter and receiver. So we call, this is what we call knife edge, because it looks like a knife. So let's call D1 and D2 the distances from the transmitter. It's actually irrelevant which is transmitting and which is receiving, because you have to think that, to keep in mind that the radio channel is reciprocal. That is, insertion losses going from point A to point B is always the same as going from point B to point A. So it is irrelevant who is transmitting and who is receiving. The channel is always reciprocal. Okay, so you go from one way to another and go back, losses are the same. Okay, so how do we describe this problem? Okay, we need some parameters for the geometry. So this is the edge of our knife obstacle. Let's call this alpha angle, and we call h the distance between the edge of the obstacle and the baseline. The baseline is the line that connects transmitter and receiver. Okay, we will not go into the mathematics of this because it's quite complex. I just give you the result. In particular, we are interested in the amplitude of the electric field at receiver. as function of E0. E0 is the field that you would receive in free space. We always refer everything to free space because free space is easy to calculate. You calculate free space and then you reduce it, because it's usually a reduction, reduce it of a given amount. So if you do all the calculation, you find that E related to E0 as the following equation. I give you for reference, but the integral from V to infinite of exponent where is V parameters is the Fresnel-Kirchhoff diffraction parameter, that is h square root of it's equivalent to the Fresnel-Kirchhoff parameter that we have seen before, just we have replaced rho with h, d1 and d2 are the distances compared. Okay, this is someone has calculated this equation for us. And if you do some if you do some mathematical manipulation of this integral, you end up with something like this. And I will don't worry, you will not won't have to calculate this. I'm just giving this as a reference. Okay, but we take this, someone has done this for us, we take this for granted. Now our real problem is what happens to the electric field. First of all, I send you some couple of graphs. One is quite cryptic, and I will project them now so we can discuss them now. This is what. Okay. This horrible thing is called corpus spiral. Is actually linked to this equation. So what is on this picture is as follows. This is the complex plane, real and imaginary parts. This is a complex equation. So this is the real and imaginary part of the complex plane. This line is a function of V. So to use this diagram, first of all you have to determine the Fresnel-Kirchhoff parameter. That depends on the geometry. So you have to calculate the definition, that's the value that is here. Once you have calculated the Fresnel-Kirchhoff parameter, you will find a point of this on this line that corresponds to that value of V. Then it can be demonstrated that this length, let's suppose that our V in our example is 0.8. 0.8 is this point. So our geometry is so that given the height, distances, etc., the Fresnel-Kirchhoff parameter is 0.8. So this length here, if you measure this length, is the absolute value of this function. So this is the absolute value, and this is the phase of this complex number. But we really are interested